when we have a series that has alternating signs, we're frequently going to compare that to the related series created by taking the absolute value. So we can revisit our ratio test and get a little bit more specific now. So if you have a series and its limit, when you take the absolute value of the ratio a sub k plus 1 over a sub k equals L, if L is smaller than 1, your original series will converge absolutely, meaning its absolute value converges as well as the original. If L is bigger than 1, then your original series diverges. And if L equals 1, the test is inconclusive. And that means it might diverge, it might be conditionally convergent, or it might be absolutely convergent. So let's try this out. I modified example 3 slightly from what was in your book to show this idea in a nice basic way. I'm going to determine whether this series converges or diverges. And you can see here again, anytime that you get that base for an exponential, which has a negative sign on it, you can expect most likely you're going to see alternating signs. And we're now going to apply this updated version of the ratio test. So we're going to take the limit as k goes to infinity of, notice again, I'm using the absolute value bars. I'm going to do a sub k plus 1, which means put k plus 1 where my k's are, all over the original a sub k. And in the last section, we learned how to simplify expressions like this using some properties of exponents. So I can take and write the expression in the absolute value bars as -2 to the k power times the -2 to the first power, instead of keeping it combined as a k plus 1. And of course, the reason I'd want to do that is it creates some cancellation with the bottom part of this fraction. I can get rid of these terms. So now I've simplified my ratio to be the absolute value of k plus 1 over k times -2 to the first power. Now, you can go ahead and take the absolute value of each of these parts individually. So in other words, I can do this. The absolute value of -2 is +2, and that limit of a constant, is the constant. So I now have 2 times the limit as k goes to infinity. And obviously, as k goes to infinity, both the numerator and the denominator here will be positive, so I can lose my absolute value bars there as well. You can go look at a graph at this point to determine this limit, or you can take one more step algebraically and separate it into 2 fractions, namely k over k plus 1 over k. That's an equivalent form of my previous step. And the reason I do that is this whole first term then becomes 1. So I have 1 plus 1 over k. I can look at each of those parts and say, okay, the limit as k goes to infinity of a constant stays a constant. This fraction, as the denominator gets bigger, will go to 0. 1 plus 0 being 1, I have 2 times 1, or 2. And remember, that's the L value. That's not what I'm saying the series converges to. It's the limit of the ratio. And now I go back to my ratio test, and my limit, since it equals 2, and that's a number bigger than 1, I've just showed the series diverges. Here's another example. I thought we'd do another one. This one's not in your book either. This one's not in your book. Again, we kind of see this -1 in there, so we're thinking, okay, this is probably going to alternate. So we'll go ahead and try our new version of the ratio test. I write out a sub k plus 1 all over what the original a sub k would look like. I guess technically I should be using n's. My original series was given in terms of n, so really I should stick with that. Not that it matters a lot. I went ahead and substituted in n plus 1s everywhere in place of the n's for the numerator and left the n's in the denominator as they were. And I'm now going to use my exponential properties to rewrite what's inside this absolute value as -1 to the nth power times -1 to the first power times n plus 1 squared. And then I'm going to again split up 2/3 to the n plus 1 the same way I did the -1. I go ahead and cancel any common factors I have in the numerator and denominator. And I have in my numerator a factor of -1 times 2/3, which would be -2/3. But because it's inside of absolute value bars, it's going to become +2/3. And I can take that outside. So I have +2/3 times the limit. I am left with n plus 1 squared over n squared. And because I have the numerator being squared and the denominator being squared, this has to be positive. So I don't need these absolute value bars here. And again, I can use another exponential property that says if you have both numerator and denominator squared in the fraction, you can sort of take that out, creating this expression. And then here's that same limit. You're going to notice we bump into this one a lot. 1 plus 1 over n. As n gets large, the fraction goes to 0. So the whole inside becomes 1. And when you square that, that's still equal to 1. So our limit is going to be just 2/3 times 1, which is 2/3. Now again, that's the L value. So now I say, okay, since my L is 2/3, and that means L is less than 1, this series converges absolutely. So I've established the convergence of my original series as well as its absolute value. All right, the last thing we're going to take a look at is a test specifically for alternating series. So this one works when your alternating series, as you can see here, does have a base of -1 inside of it. And two things need to be true in order for you to use the alternating series test. And it's important to note here that C1 is just that first value. C2 is independent of the sign in front of it. So when we say C2, like for instance, if this was that alternating harmonic series that we started with, which look like this, when I report my C1, I would say it's 1. And when I report my C2, it's what comes after that subtraction sign. So it's just 1/2. My C3 would be 1/3. My C4 would be 1/4. Okay, so please understand that when you're looking at these C's and comparing them, you're doing that independent of their sign. And again, what this part says in symbols is the terms are getting smaller. And they should be approaching 0 is the second condition. So if we go back to this alternating harmonic, we have 1, we have 0.5, we have 0.3 repeating, we have 0.25. I can see that my terms are definitely getting smaller, and these values are converging to 0. So the terms are getting smaller and heading to 0. If that's the case, the series converges. And there's a statement here about what the sum of that series is going to look like. It's not particularly important for this class that we use that part of this test. The important part is just figuring out, does it converge or not? So in example 6, determine whether the series converges or diverges. So again, your brain is going to see this often where you say, oh, I've got a negative base. This is probably going to be an alternating series. So I'll just go ahead and use the alternating series test. Well, keep in mind, you've got to verify that those two conditions hold, namely the terms are getting smaller, and number two, that they are heading to zero. So do not just automatically apply the alternating series test anytime you see a negative base number. So let's write out a few of these terms so we can figure out what they're doing. So the first term, C sub 1, I would just substitute 1. And again, I'm going to disregard the sign. So I really don't need to pay attention to this term because all it's going to do is alternate the positive and negative. I really just need to substitute here. So I have 1 over 1 plus 1 is 1 over 2. C of 2, and I get 2 over 3. And then for C of 3, I'm going to get 3 over 4. And if you look at the values of these terms, you can see they're not actually getting smaller. In fact, they're increasing. So neither one of these statements is true. They're not getting smaller and they're not heading to zero. Therefore, we can't use the alternating series test. So the question then becomes, what do we do instead? And this is where I'm going to introduce something I created for you. This flowchart lists all the different tests that we've learned and gives you a suggested order to go through them and explains what to look for and what the result means. So I'm going to try the nth term test, and I'm going to look at the limit as n goes to infinity of my a sub n's. The C's disregard the signs. However, when I want to apply the nth term test, I need the actual a sub n's. I need a sub 1, which is negative 1 to the first power times 1/2. So that'll be negative 1/2. And then I need a sub 2 will be negative 1 squared times 2/3. So that one's going to be positive. The next one's going to be negative, and so forth. And now I look at the limit as n approaches infinity. As I write out more and more of these terms, what are they approaching? So I've now asked Mathematica to go ahead and create a table of the a sub k values. So these are the individual terms. And I've had it write out the first 100 of them. If I ask Mathematica to calculate the limit of the a sub k's as k goes to infinity, you'll notice it says indeterminate, because from the table, the even k values are approaching positive 1, but the odd k values are approaching negative 1. So because of that, there is no limit. And if the limit doesn't exist, the nth term test says the series diverges, because the only time the series can converge is if the limit of the a sub n's is equal to 0. And we'll do one last example. Now you can do this by just starting at the top of the flowchart as you saw before. Or again, you're going to start to recognize some of these series and think, well, maybe I'll just apply that most likely test first. So I'll probably be tempted to apply the alternating series test right away. Now, again, when you generate and look at the terms of the series, we're looking independent of the part of the formula that is generating the positive and negative signs. So here I would begin with C sub 2 because n is beginning at 2, and that would just be 1 over the natural log of 2. C sub 3 would be 1 over the natural log of 3. C sub 4 is going to be 1 over natural log of 4. And I need to check out these values and make sure that they're decreasing. So the first one is approximately, I should say, 1.442. Then we have approximately 0.910, then approximately 0.721. So it does appear that the terms are decreasing. And then are they approaching 0? So I'm in Mathematica now, and I've stored c of k as the function 1 over the log of k. So again, I'm ignoring the part that's controlling the sign of each term and just getting the value of each term. Here's the first 100, and they are decreasing. Now, what number are they headed towards? Well, I can ask Mathematica for the limit as well, and you'll see that the limit that it came up with is 0. So we've met the two conditions for the alternating series test. Since the c sub n terms are decreasing and the limit as n goes to infinity of the c sub n's is 0, I know the series converges. So that's how to use the alternating series test.